and welcome to today's session. So today we'll talk about linear regression and how do you implement it in the KNIME's analytic platform. So KNIME is an open source platform that is a drag and drop tool to use machine learning and other algorithms. The benefit is that it takes away the time you invest in coding and then you can focus more on the algorithms. Also, since it's a drag and drop tool, it helps the people that are not from tech implement these algorithms without much learning. Also, the dataset I'm using is an open source dataset that is available online. I'll add the link to the description as well. So the first thing that we have to do is we have to read the file. There are nodes in KNIME that you can search from the left side, and you want to read a CSV, you can just type CSV and it gives you a CSV reader. However, one more thing about KNIME is it is quite intuitive. So rather than adding the node, I can just look at the file. So I'm going to use the startup file and drag this file to KNIME directly. It will automatically open the CSV reader with the link in the URL file, and you can look at the file directly in the preview. So while looking at the file, I can see that I have 5 columns, and all of these columns are properly ingested in the system. I click OK and execute this. So remember, whenever you click OK, it does not automatically execute the node. You have to execute it separately. I can right click on the CSV reader and look at the file tab. Now, if you look at this file, I have 4 columns and a 5th target column. The 4 columns are R&D spend, administration spend, marketing spend, the state the company is situated at, and their profit. And what we're trying to do is we're trying to predict the profit using the columns that are independent. These are R&D spend, administration, marketing, and state. However, we all know that the first and the foremost thing that you need to do is to look at the missing values. For this, we can look at missing value node, and there is a column filter called missing value column filter. So there are 3 ways you deal with missing values. The first one is if there is a column that has a lot of missing values, like 90% or 85% or 95%, you omit the column from the analysis, and that is what this thing will do. So I'll connect the CSV reader to this and configure the missing value column filter node. I'm trying to look at all these variables, and I'm saying that if any one of them has more than 90% of the missing values, we need to exclude them. I can execute this and look at the filter table by right clicking. You can see that it has not excluded anything because almost all the columns are filled. The next thing that we need to do is look at the row wise missing values and see if we need to exclude any row. So again, by principle, if there is any record that has a lot of missing values, you better omit it rather than fixing the value. So for this, we'll use column aggregator. What it does, it aggregates all the columns by a certain aggregation function. We'll connect the output of missing value column filter to the column aggregator, right click it and configure. We want to use all these as the columns, and in options we want to select the missing value count. I can add this and it will be missing value count. I'll click OK and execute this. If I open the view, I can see that it has added a column in the table which is counting the number of missing values. So in this row number 19 we have 1 missing value, in row number 47 we have 2, and in row number 48 and 49 again we have 1 missing value. Let's suppose I want to remove the rows that have more than 1, that is 2 or more missing values. For that, I'll add the node called filter rows, row filter, and there I'll connect it with the column aggregator. I'll configure this and I'll say we need to include or exclude the rows by attribute value. I'll use the column missing value count, and for anyone that has 2 or more missing values, I'll exclude it. If I right click on this and execute, then look at the filtered column. I can see the row number 47, which has two missing values, is now excluded. So in the start I talked about there are three ways you can work around missing values. First is removing the columns that has a lot of missing values. Second is removing the rows that have multiple columns that have missing values. And last is now imputing the missing values. There are multiple ways you can impute. In KNIME, you use missing value node, you connect it with the raw filter and configure this. It will give you two things. A, by the type of the column, if you want to do something, it can be either a fixed value like 0 or 10 or whatever you want to do this. It can be mean, median, minimum, moving average, and a lot of other values. We'll cover all these in other chapters. For now, we can say if a certain office or a certain company has no value in a certain spend like R&D spend, administration, or marketing spend, we'll impute this with the minimum value. We can impute this with 0 as well, but we'll say whatever the minimum spend of all these company is, the spend is of the missing value as well. We'll do nothing on the string because we saw that there is no issue in the string, and we'll do nothing on the number, or we can just use minimum, just like this. We'll click OK. Remember, you can also use columns and do this thing separately. Like you can do, for this you can do a fixed value, for this you can do a maximum value, and also so on and so forth. But right now we do not need to go this far. Click OK and execute. Now if you look at the output table, you can see the column with one missing value has now imputed the missing value as a minimum. Similar, the 48 and 49 rows are also filled with minimum values. Let's now move to the linear regression. But before that, we also know that we do not train the linear regression or any supervised learning model to the whole dataset. So for that purpose, we'll have to divide the dataset into two sets or subsets called training and validation. For this, we will use the partition in KNIME. So I'll just drag the partitioning and connect the output of this node to this partitioning node. I'll configure this. We can either use absolute like number of rows or relative, which is percentage. So I'll use 70% as a training data and the rest 30% will be the test data. Also, it gives you an option of taking the rows sequentially, drawing randomly, stratified, and linearly. For the purpose of randomness and keeping it representative, we'll use random sampling. You can also use random seed. Now what this helps you do is that if you want to repeat the experiment, you can enter the same number that I have entered here and see the same results. It is good to do because when you do the analysis and you come across something astonishing that you want to tell to someone, you cannot go back doing the random sampling again unless you have the seed. But with this seed, you can just put the number in this random seed and the same random sampling that you did in the previous experiment will be repeated. We click OK and partition the table. You can see now they have two output nodes. The first partition has 34 columns or 34 rows and 6 columns. The second one has 15 rows and 6 columns, which is 70-30 partitioning. For the linear regression learning, we'll use linear regression learner in this KNIME, and for prediction, we'll use regression predictor. We'll connect the first node with the learner and the second node with the predictor. Lastly, we'll connect the model that we have developed from the learner to the predictor so it knows what is the equation. We right click on the learner, do configure. Now if you look at this thing, we had 6 columns. As we did an aggregated value, it is also coming in this options. We know our target is profit and our independent variables are R&D spend, administration spend, marketing spend, and state. We can omit this by double clicking or clicking this arrow. So now we have 4 independent columns and 1 dependent column. So it has 2 options. One is ignoring the rows with missing values or failing on the observing missing values. Since we have already taken care of the missing values by imputing them and deleting the rows, we do not need to ignore the rows. Click OK and execute. When you execute it, you can right click on the linear regression learner and look at the resultant view. The resultant view will give you certain characteristics that you can observe and work around. The first is the R squared. In layman's term, it is the accuracy of the model, and here the accuracy is 96%. The second is for each variable, it gives us the coefficient which will be used to develop the equation. So here the equation will be something like 50,000 plus 0.82 multiplied by R&D spend plus minus 0.01 multiplied by administration spend plus 0.0196 multiplied by marketing spend, and so on and so forth. However, we all know that for linear regression model, we also look at the significance, which is the last column here. And the p-value should be looked at. If it is less than 0.05, we keep it in the model. If it is more than 0.05, we omit it. The way to do it, it is sequential. So instead of omitting all the values, we look at the highest p-value. Currently, that is administration. So we close this window, right click on this, configure, and remove the administration from the input variables. Click OK and rerun the node. Look at the data again, and you can see the p-values have now changed. However, the state p-value is more than 0.05 and is the highest among all 3 variables. We'll again configure this, remove the state, click OK and execute. When you look at the resultant view, you can see the p-value has shifted slightly. However, across all these things, one thing that you have noticed is that R square or adjusted R square, which is our accuracy, has not changed, which means those variables were not significant in providing the value in the regression model. If you look at the marketing spend, it is still higher than 0.05, so we'll exclude that as well. We'll right click on this, configure, and remove the marketing spend. Now please note that it is not always that you will be remaining with one variable. Sometimes 2 variables are there, sometimes 4 variables are there. It depends on the model you are training rather than a thumb rule. You can click on the resultant view. You can see our accuracy is still intact, 96%, and our equation has simplified greatly. So our now equation is 49,602 plus 0.85 of the R&D spend is our actual profit. Now since we have developed the model, we can use this model and execute it on the testing data. We have already connected the node of second partition to the input and the model to predictor. Right click on this, execute, and look at the predicted data. So if you look at the predicted data, you can see the profit and predictions are very close. Hence, it is proving that our model is working fine. The other way to look at this is to calculate the R square of test data as well. For this, we'll use the prediction in the profit and calculate it manually in the Excel. So we'll use the first and the second column. The first one is the actual profit, the second one is the predicted profit, and we'll use 2 more columns to add the R square. The first one is squared error. that is profit minus predicted squared, and you can track this. The second is squared difference from mean. For this purpose, we'll use the profit, and instead of subtracting from the predicted, we'll subtract it from the mean of the first column, that is A. Now what it is doing, it is trying to differentiate of how the model has impacted the prediction. If I would not have built the model and only used the average as the output, would I have resulted into the same thing or an improved version? So that effort is determined by this type of comparison between squared error and squared difference from the mean. Let me compare this, drag it. The next thing you have to do is sum squared error and squared difference. Lastly, to get the accuracy, you divide the squared error from the squared mean and subtract it from 1. So you can see our accuracy is 90.6%, which is similar to the trained data.